Good day and welcome back for the fourth and final part of our discussion related to limits at infinity. And let me once again give you kind of a bigger picture reminder. Our short-term goal, and what we will get to in our next section, is using properties of calculus and a few borrowed properties from algebra or pre-calculus to accurately sketch the graph of a given function. Using things that we mentioned in our previous section related to intervals of increase, decrease, concavity, classifying critical points as local maxes and mins, really allows us to take care of the middle portion of the graph. To take care of what's happening way to the right or way to the left, i.e. find these horizontal asymptotes, we need to be able to investigate limits as x approaches plus or minus infinity. In this section, we introduced a new limit law related to limits at plus or minus infinity, as well as a nice property that allows us to quickly and efficiently determine the limit of a rational function, with essentially showing no work whatsoever, just a small justification. And as we continue on with an additional example different from, say, a rational function, it's worth noting that our previous limit laws, as long as they make sense to apply, we certainly can do so. And what I typically mean by saying that they make sense is that you end up with quantities that are well defined, not something like infinity minus infinity, infinity over infinity. You're not dividing by zero. So to give this some context, let's consider the following example. The limit as x approaches infinity of the square root of the quantity 9x squared plus x minus 3x. What I want to observe is for a large value of x, this quantity square root of 9x squared plus x is getting really, really large, i.e. going to infinity, and 3x is also going to infinity. So this quantity is essentially appears to be going to infinity minus infinity. And there is a natural kind of inclination to look at that and say, well, of course it must be 0. But remember, infinity is not a number, and we cannot treat it as such. And what that means is we need to instead go through and evaluate this using limit laws. And what I want you to think about is, what is a technique we've previously encountered when we had something that involved square roots, but we could not directly apply our limit laws? And hopefully you're thinking of this conjugate over the conjugate technique. What we are going to do in this case is see if we can revive that technique, and we'll multiply this by 1 in a fancy way. We'll take the conjugate of the quantity in the top, so change that minus to a plus, and so that we're not changing the value of the limit, we have to make sure that we multiply by 1. And just the quick reminder to the side, if you have two conjugates, so say a plus b and a minus b, when you distribute everything out, that's simply a difference of squares, a squared minus b squared. So in our case, in the bottom, we're left with that quantity we're multiplying by. That's not going away. But in the top, note that we have a minus b times a plus b. So precisely why we have multiplied by the conjugate over the conjugate. So we get the first term squared, i.e. that square root goes away, and we subtract away from it the second term squared. So we're subtracting away 9x squared. And this works out wonderfully because you have a negative 9x squared and a positive 9x squared. And now just rewriting this to get a better look at what we're working with. In the numerator, we're only left with an x. And in the denominator, we have this quantity square root 9x squared plus x plus 3x. And we kind of ask ourselves again this intuitive question. Can I just use my limit laws? That would be the limit of the top over the limit of the bottom. And the unfortunate answer is no, because you would get infinity over infinity, which has no meaning associated to it. But remember our previous intuition. We can simply think of the largest power of x in the bottom, and we can multiply by 1 in a fancy way. Now, here we have to be a bit careful because it's not just the largest power of x, you also have to account what is being done to it. So you have an x to the first, and you have an x squared. But note the x squared is underneath the square root, which really indicates it's going to behave just like x to the first power. So our technique of multiplying by 1 can still be applied. The largest power of x in the bottom, taking into account everything that's going on, is 1. So we will multiply by 1 over x, divide it by 1 over x. So let's go ahead and let this all distribute through. In the top, things work out quite nicely. X over x is just 1. In the bottom, I'm going to do this in 2 steps. We have the 1 over x hitting the 3x, which is just a 3. But we also have the 1 over x that's going to be placed right up next to that square root term. So when we have that 1 over x hit the square root of 9x squared plus x, we want to nicely combine and get some cancellations. The only way we can do that is if we rewrite the 1 over x as a square root. And note, this is precisely what we were talking about in our previous video. Since x is going to infinity, we can assume x is a positive quantity. And when x is a positive quantity, 1 over x is the square root of 1 over x squared. And just as a reminder, and I'll let you think about it, if x was negative, i.e. if we were going to minus infinity, how would you have to modify this formula? So combining together those remaining terms with x's in the denominator, we would have a square root of 9 plus 1 over x. And note that 1 over x is coming from x divided by x squared. And then still a plus 3. And we cannot simply plug in x equals infinity, right? Or simply say the answer is 1 over 6. It's not a rational function. We need to really take into account our limit laws. And I know sometimes it seems tedious, and typically what I tell students when they kind of complain saying, do I really have to show these steps if I know what's happening? My response is almost always going to be, those should be the steps you're happy to show because you know exactly how they're going to work out, and they'll probably be the easiest points for you to get in the entire problem. So we're using good notation, we're organizing our work in a nice logical fashion, and we're showing all of these steps. So take a limit of each and every term, and while we're at it, we throw that limit underneath the square root and break it up. And the reason we do this is now each and every one of these remaining limits is quick and easy for us to evaluate. The only one involving an x goes to 0. And let me give you kind of another reminder to the side. We saw with our limit law, as long as r is a positive quantity, the limit as x goes to either plus or minus infinity of 1 over x to the r is equal to 0. And then our case here is r equals 1. So what we are left with is 1 over the square root of 9 plus 0 plus 3, which is 1/6. Once again, kind of connecting this back up to the starting point, remember we saw that intuitively this looks like infinity minus infinity. And note, you really cannot say infinity minus infinity is 0. In this case, it happens to be 1/6. Because remember, infinity is not a number, it's this kind of idea or concept. Lastly, let me also note, if you were asked to find the horizontal asymptote of this function we started with, I would like you to pause the video and take 10 seconds and write down what is that horizontal asymptote. And hopefully you've done that. Remember, a horizontal asymptote is a line. So it would be y equals 1/6. And finally, in our next section, we will combine together these previous 2 sections to accurately sketch the graph of a function. So stay tuned and take care.